Good morning, students. Welcome back again with our topic Geotech Engineering. CE 701 is the subject code. Today we will discuss about the topic soil consistency of the Geotech Engineering. So let's start. So basically, soil consistency is that definition or a term which indicates the degree of firmness of fine-grained soil, in which generally expressed in terms of very soft, stiff, very stiff, and hard. Basically, when the soil behaves, when we add water into it, or the moisture content increases or decreases in the volume, then how it behaves we will discuss here. The soil behaves like solid at very low moisture content. As we all know, if there is very low moisture in the soil, then it will behave like a solid. If the soil have high moisture, then it will behave like a liquid. So in the figure you can, or we can say in the pictures, you can easily see when the moisture content is low, the soil will look like a solid, and if the moisture is very high, then you can see it looks like a liquid. For understanding consistency, Atterberg has given some consistency limits which defines the consistency of soil very precisely. If we generate a graph between volume of soil and moisture content, then we will get a graph in which if we add water into the soil at a volume, then we can see the soil will behave like a solid when the volume will be remaining same and moisture content is increasing. But at some point, or we can say at a sinkage limit, the volume of the soil will also increase as we increase the moisture, and which will gradually get increased to a level. Basically, there are four types of we can say soil, or we can categorize into four types according to the moisture content. The first one is solid, the second one is semi-solid, the third one is plastic, the fourth one is viscous liquid. If you can see at a solid part, the volume will not increase when we increase the water content, but at a point volume will also increase when it becomes a semi-solid, when we increase the water content. So here you can see up to plastic limit, you can say the soil will behave as a semi-solid, but after plastic limit it will behave like a plastic. So up to liquid limit it will behave like a plastic, and after that it will behave like a viscous liquid. So there are three types of limits which defines the soil or defines the behavior of the soil. These are sinkage limit, plastic limit, and liquid limit. So what is liquid limit? The denomination for liquid limit is LL or WLL. Liquid limit is defined as a moisture content at which soil begins to behave as a liquid material and begins to flow. Basically, if we increase the moisture content in the soil, when it behaves like a liquid material, or we can say it starts flowing, then we can say the soil has got its liquid limit. Liquid limit of fine-grained soil gives the moisture content at which the shear strength of the soil is approximately 2.5 kN per meter square. So this is the liquid limit determination experiment, which is known as Cassegrain apparatus. Here you can see in this apparatus there is a ball in which we take some soil sample and add some quantity of water in it in a percentage, and then just cut that soil sample with a stick, or when we move this ball in the instrument, it will you can see it starts to join each other. So at that point when it joins, we can note the reading, and we can get the liquid limit of the soil. In liquid limit determination, there is the first method, which is known as 3-point method, in which liquid limit is the moisture content requires to close a 2 mm wide groove in a soil pad a distance of 12.7 mm along the bottom of the groove after 25 blows. So we start the instrument and we started the blows. After 25 blows, we just see the this part which get joined together, and determine the liquid limit of that soil. So here the graph between moisture content and number of blows taken for liquid limit determination. As you can see, liquid limit is equal to 42 if we get 20 means that after 25 blows we get the liquid limit is 42 with the help of flow curve. The second method for liquid limit determination is 1-point method. Here you can see liquid limit will be defined by the formula, in which liquid limit is equal to Wn upon into n upon 25 bracket tan beta, where n is equal to number of blows, W is equal to corresponding moisture content, tan beta is equal to 0.121. So in that, assume a constant slope of the flow curve. The slope is a statistical result of 767 liquid limit test, Norman 1959. Limitations of that this method is tan is an empirical coefficient, or we can say tan beta is the empirical coefficient, so it is not always 0.121. Good results can be obtained only for the blow numbers between 20 to 30. So if you want to get the very actual or precise value, then you have to work on the blows, that is you have to take blows up between 20 to 30. And the empirical coefficient, we as also discussed, it is not always same as the tan beta is an empirical coefficient. This is the flow index by which we get the we can say the IF value of IF is equal to WL minus W1 minus W2 upon log N2 upon N1. Larger the IF value, smaller will be the shear strength of the soil. Now, what is plastic limit? Plastic limit is defined as the moisture content at which soil begins to behave as a plastic material. So, plastic index can be known by liquid limit minus plastic limit. So, the graph is same as we have discussed it in previous slides. So, determination of plaster limit is moisture content at which the soil rolled into threads of 3.2 mm in diameter with crumble, where PL is equal to water percentage at 3.2 mm diameter. The last is sinkage limit. Sinkage limit is defined as moisture content at which no further volume change occurs with further reduction in moisture content. So sinkage limit is equal to Wi percentage minus delta W percentage. Sinkage limit can be also known by this formula, or can be determined by the formula SL is equal to WI percentage minus delta WI percentage, in which WI percentage is equal to M1 minus M2 upon M2 into 100, and delta W percentage is equal to Vi minus Vf upon rho W upon M2 into 100. So if we put the values, both of the values of Wi and delta W, then we can get shrinkage limit. This is the plasticity A-line chart which we get, in which you can see if we divide this chart into two parts, then the area or we can say liquid limit is equal to 50%. Then if it is lower than 50%, then it is low plasticity, and if it is higher, then it is high plasticity. So that's all for today. Thank you very much. Have a nice day.